Hi, I'm Adam, and this is my 16-bit computer from scratch. At the moment I have my control logic mid-plane working perfectly, but I do have a couple of bodges on my control logic control circuit that I'm going to have to clean up at some point here. I have my reset circuit and my clock module prototyped out on breadboards. With the build at this point, I was actually able to achieve some stability in the last video, where the circuit resets and copies the control signals from serial EEPROM to parallel SRAM. Off camera between videos, I did change all the resistors on the LEDs from 1K to 10K. I did this so I don't blow out the camera exposure. My goal is to make this a little bit easier to see which LEDs are lit and which ones are not. Interestingly enough, it had a rather dramatic effect on the power consumption of the circuit. Prior to the change, it was consuming about 1500 milliwatts or 1.5 watts of power. Now it's less than 500 milliwatts. Starting with this video, I do want to change the format a little bit. I want to move away from the drama of me not having a clue what the heck I'm doing and get a little bit more into the thought of completing a task in each video. I'll still share the struggles with you, but I'm not going to spread that drama out over several videos, unless I really need to. It will certainly be the exception if I do. I'm also going to start doing a little bit of prep work ahead of each video just to make sure that things move a little bit faster. Please let me know how you feel about these changes in the comments below. If you really like watching the train wreck, I'm not opposed to it. I'll find a way to make that work so that you can enjoy that as well. This is my fetch register and my instruction register prototype from the other build. I'm going to salvage this and bring it into this build. It worked reasonably well, but there are some things that need to be updated in order to make them work here. More on those changes in a moment. But in this video, I will be retrofitting the fetch register and instruction register and placing them into this build. At the end of the video, I will be executing no-op instructions. Why a no-op instruction? A no-op instruction is what's going to be executed when nothing is presented from the memory module. Okay, let me clear some room and we'll get started. Before I took the rest of the build away, I thought I'd check and see what the power consumption was for these boards and what it actually added to the rest of the build. It's pretty significant. Hopefully I can clean that up just a little bit. I managed to get a little bit of prep work done ahead of this, and so I've got LEDs, resistors, and some wires cut so that I can drop them into place quickly. I'm going to start with these 1K resistors down here. These are pull-down resistors for the fetch bus. I think 1K is probably a little bit strong to pull down, so I'm going to switch those out for 10Ks. This is the instruction that's coming out of memory into the fetch register that it's to be executing. And if the memory module doesn't present anything, then I want that to be a no-op instruction by default and let the memory actually override that. Next, I want to replace the LEDs with one of my utility PCBs that has 16 LEDs plus resistors on it. Doing this allows me to eliminate these 220 ohm resistors for the LEDs. I now have 10K resistors on the back of that PCB. I'll just move that and deal with that here in a minute. Okay, this is the main bus output. It's got pull-down resistors, which are already 10,000 ohms, for pulling down those signals in case we're asserting a 0 out onto the main bus. This is ALUB. It does not have pull-down resistors yet, but it will. This is the instruction bus. It also has 10,000 ohm pull-down resistors for pushing a no-op in case the fetch register is not pushing anything onto the instruction bus. This will happen when there's an immediate value that follows an instruction. Finally, this is address bus 2, and again, not used yet. So other than the control signals down here, the fetch register is cleared up. But what I want to do is I now want to get up here into the instruction register. Now in my build, the instruction register really doesn't do too much other than provide a visualization of what's going on in the control logic midplane. So these LEDs can actually be driven by the latch because there's nothing else that it actually does. And so I'm going to pull these line drivers out and I'm going to reposition LEDs up here. I'll start by pulling the connections to the LEDs, then the line drivers themselves. And here's the new LED PCB. Next, I'm going to move the hookup wires over so I have 16 consecutive rows for the LEDs. Hopefully I got all those in the right order. I gotta make sure I test that. Next, I have 16 connections to ground I've got to make for the cathode side of the LEDs. And finally, I can remove the old LEDs and the resistors. All right, so we'll start with address bus 2 assert. And then the instruction suppress, the only one that is not going to be inverted. Uh-oh. Yeah, that made a mess. All right, let me get these pushed back in. With any luck, I get them back in the same sequence. I'm going to have to make sure I test that as well. All right, ALUB, main bus assert. Don't need that hookup wire. And finally, the clock signal. Now I can get rid of the line driver, the LEDs, and their resistors. The hookup wires for the LEDs, and the miscellaneous signals for ground and VCC. Let me define the new interface points with ground and VCC. Then I will have my inverters, my line driver to drive the LEDs. Let me move this cap over. And so I can keep them straight, I'll label the signal LEDs. We'll see how long that stays there. Power and grounds. Cathodes for the LEDs. I'm only going to use 4 of the 8 signals here on this line driver, so I'll tie the rest of them low. Okay, now to rebuild these control signals. I'll start with clock. Now the clock is already wired all the way up to these latches here, so that's good. Next up is instruction suppress. Instruction suppress is actually used in its native form, and it does not need to be inverted. So that is trivial to hook up. And then I'm going to extend this over to the line driver. And then from the output of the line driver up to the LED. Next up is the main bus assert, which will come in here, but it's an active high signal and the line drivers require an active low. So I'll bring that over to an inverter and then extend that beyond that over to the line driver so that its output can drive the respective LED. And then the output of the inverter, which is now an active low signal, will come up here to the line drivers for the main bus assert. ALU bus B assert has a very similar story. So I'm going to extend this over to the inverter and continue that same signal on to the line driver, where the output will light the LED when the assert is active. And then the inverted signal will come up here to the actual output enable. The final connection is address bus 2, which needs to be extended to the inverter. And then from the inverter on to the line driver so that its output can drive an LED. And then finally, the inverted output hooked up so that it drives the line drivers. Now, the final thing I need to deal with here are the unused gates on the upper side of this inverter. And I'm a little tight up here on space, so I'm going to tie these high rather than low. I just need to tie them to some known voltage, or some known state, I should say. There we go. Let's test it. Okay, for testing, I need to deal with these inputs. Now, I've got 4 control signals here. This is on TTL compatible inputs between the HCT and the LS logic. So these have internal pull-up resistors on the actual ICs. I need to be able to drive these positively, either high or low, to make sure that I'm getting the correct signals here. So I'm going to start by hooking those up, and everything coming off of the control logic midplane is an active high signal. So I'm going to start by making them all low. This is the default for every signal coming off the control logic midplane. I also have a clock here that I'm going to set up, and that's just going to be low for the moment, and I will manually move that high and low as I test. And then I need power, so I will put in power and ground leads, and then hook that up to my bench power supply. When I apply power to that, I'm pulling about 200 milliamps, so the TTL logic actually does consume quite a bit more power than the HC logic does. I'm well over a watt here. Now, if I was to make, say for example, address bus 2 assert go high, you can see that LED comes on. Next one is instruction suppress, and that next LED comes on. Next one is the ALUB assert. You can see that LED come on. And the final one is main bus assert. Now, I've got down here, everything is tied low by default. This is the input off the fetch bus into the fetch register. And if I was to clock that, that 0 then clocks into the instruction register. Now, if I was to take a bit at random and tied it high, and then another bit at random over here and tied it high, next time I clocked, you can see it shows up in the fetch register. And I'm willing to bet because of bouncing, it also showed up in the instruction register. In other words, I don't believe that it's actually latching both of those at the exact same time. And I do believe that is bouncing, but I will... Yeah, that's definitely bouncing. So in order to test this, I really do need to get out my single step clock and make sure that I can actually test this properly with a properly debounced clock signal. Here's the rest of the build, and I'm only really interested in the single step clock in the bottom right hand corner of the clock module. Let me get power and ground. And then the hookups to the bench power supply. The last connection to make here is for the clock. Now I'm going to drive the clock directly from the output of the single step debounced. I would drive it from the CPU clock up here, except that there's some issue here that I just uncovered, and I'm not going to spend any time working on that on camera. I'll report the results when I find it. Power on, single step mode, and now if I step the clock once, my value moved to my fetch register contents moved up to my instruction register. If I clock again, I now have the same in both. If I take instruction suppress and make it high, I can set a new fetch register value, but nothing moves on to the instruction register. That ends up being a no-op instruction. And say, for example, if I am asserting out onto main now, this value should be visible out on the main bus. And then it's just a matter of going through with the logic probe and confirming that my highs are high and my lows are low. I have to do that because I did make a bit of a mess here with some of these connections. I'll do that off camera. That way you don't have to sit through that. Back in a minute with those results. Okay, I spent a little bit of time with this. Here's what I found. This IC was bad. This first inverter gate here had no output, so this was always presenting a high impedance output. So therefore I could not get the main bus to assert. I replaced it with a new one. It works just fine. As for the messy signal integrity causing the single step clock to latch the fetch register on the low going edge, I started by trying a 10 picofarad capacitor connecting that signal to ground in an attempt to try to push some of that noise off to ground. That didn't work. I pulled it back out. I tried putting a low value resistor in line like I did over here. That didn't work. I pulled it back out. I ended up asking ChatGPT and the suggestion came back to use a 100 picofarad capacitor here, as I had tried before, but just a larger capacitor value. The 100 picofarad capacitor worked, so that's cleaned that signal up. I think I'm going to have better luck once I get away from the TTL compatible inputs here and get this onto PCB. But I am going to add a place for that capacitor in case I find that I actually need it. And then I'll just insert a 1206 capacitor in there in order to pull that down if it's absolutely required. I also went through and did tests of all of the outputs to make sure that each pin was showing up on each output appropriately, and I'm good there as well. So that wraps up the initial tests. So this module now is ready to go and be integrated into the rest of this build and see if I can't actually start executing NOP instructions with what I have here. To be able to complete this integration, I actually have some prep work I have to do on the control logic midplane to add all the connections I need for the fetch and instruction register. Let me extract this so that I can start working on it. The first order of operations here is going to be to add capacitors to the power connectors over here on the side. I've got this power connector that does not actually have a capacitor on it, so I want to rectify that as well. Pull this out of the way just for ease of access. Okay, next up I want to add these 4 power connectors here so that I can then hook up the breadboard to these. Okay, the last connection to make here is going to be down here. This is where I need to pull all of the control signals for the fetch register. Okay, that prepares the control logic midplane for integration. Here's the build laid out side by side. I don't have anything connected back up yet. I'm likely going to need some kind of an intermediate board down here. I'll show you that when I get to it. Over here I've got my clock and reset circuits. Over here I've got my fetch and instruction register, and of course my control logic midplane in the middle. I just added a bunch of power down the side here so that I can connect that up easily to the 2 registers. I may need more power between these 2 because it's got to travel all the way over here as well. More on that here in a minute. And now this signal I need to get all the way over here to this clock. So I am going to grab this board and basically create just an intermediate jump point. Hook this up to my power supply. This is now the output from the fetch register, the input into the instruction register. It also becomes the input into the control logic midplane. So the last thing I need to do is I need to hook these up. Let's do this. That should make things just a little bit easier here. My instruction suppress is up here. Instruction suppress. My main bus assert is here. It's the 3rd pin in, and that needs to come over here to that location. That's tight, but that will work. My ALUB is the 2nd pin from the left. And then address bus 2 is the last pin. Now, I'm not going to say this looks great, but at least it contains all the connections that I need. I can probably reduce the size of this. And that allows me to bring this in a little bit closer. The other thing that may allow me to do is take another power and ground and bring those signals. Okay, now I just need a quick sanity check to make sure that power and ground haven't been cross-connected. And they have not. All right, place your bets. Think this is going to work? Okay, so I do have one bit that's still hooked up high. That bit is reflected here, and that bit is reflected up here. If I put this now in single step mode, I can control this a little bit better. And if I pull everything out of what would be then the fetch bus, I should have a no-op that is latched into the next clock cycle, and it is. Now that now means that there's a no-op instruction that is being processed by the control logic control, getting ready to be presented by the control logic modules themselves. If I clock again, this now goes to a no-op. All of the lights turn out here, and I am expecting one of these to be lit. I am expecting a program counter increment to be lit. Okay, I have found that EEPROM C7 did not have its full programming. So let's try that again. And again, I'm latching no-op instructions, and I am now getting my program counter increment. And again, if I go back to single step, that's working perfectly. Now, high speed, I don't expect anything different. Now, what I can do is I can tie one of these high momentarily, and I may or may not get something different here. But that all looks like it's working brilliantly at 5 megahertz so far. Now, I did also find that I do have voltage drop pretty significant from where power was coming in here and all the way over here to the far corner. So what I did is I ended up ganging this up here so that I have the same power here on the breadboard as I do here on the PCB. And then I can add additional connections here to make sure that I've got good power. I'm okay. I'm about 4.8 volts down here in the corner. I could add additional connections, but as things stand right now, it's running. So that's a good thing. Now, if you're paying attention, you'll be screaming at the screen at this point, yelling, Adam, how can you call this executing no-ops? You don't have a program counter register in the system, therefore there's nothing to increment. And you're right. But what I am getting here is with every one of these clock ticks, I am getting the instruction, what would be the instruction, advancing along the fetch register into the instruction register and getting the, let's see here, I think one is something different. And then getting the control logic to update accordingly. And then when I run that, that's working perfectly. Wait, Adam, why is it flashing? Actually, because that's a move immediate instruction. And instruction suppress is also coming on. That's the third LED over. So instruction suppress is always also coming on, meaning that it is suppressing the move of the value from the fetch register into the instruction register, and I end up with a no-op every other clock tick. I actually think that's pretty cool. So if I pull that out, I'm getting straight no-ops. Not executing, because technically it's not incrementing a program counter. But I'm going to call that a win and call it close enough. In video 101, I made a number of updates to the fetch register. But I did end up with an error on the schematic that I noticed as part of prep for this video. I figured I'd take a minute here to fix that. And what was that error? Well, the LEDs here are tied to VCC, but they really actually need to be tied to ground. That is as simple a change as that. Well, this is still quite the milestone for the new build, even if I don't have a proper no-op instruction taking place. I'm even able to run the clock at 5 megahertz, where I can still feed instructions in manually and have them progress into the fetch register and on up into the instruction register. As you may notice with today's video, I'm skipping a bunch of the drama related to me not having a clue what the heck I'm doing. What I want to do is focus on accomplishing a single task in each video. There's a risk here that I may not be able to publish videos as quickly as I have been in the past, My hope is that the trade-off is that I can hold your attention a little bit longer. So let me know in the comments how you feel about these changes in the video format. If you like the drama and like seeing the train wreck, let me know that as well. I'll figure out a way to incorporate that in. Now for the next video. I'm going to be pulling out the botched program counter and the program ROM memory from the old build. These two additions will overcome the issues with the NOP instruction, but above and beyond that, I plan to add both a break and a jump instruction into the mix in the next video. Lots to look forward to. We'll see you soon. My wife Carrie has been working on a cookbook. Carrie's cookbook provides a unique culinary experience by seamlessly incorporating doTERRA essential oils into a diverse array of mouth-watering recipes, transforming ordinary meals into extraordinary dining adventures. The cookbook offers a treasure trove of innovative dishes that combine the health benefits and aromatic richness of essential oils with fresh, wholesome ingredients, making gourmet cooking accessible and exciting for everyone from novice home cooks to seasoned chefs. Each thoughtfully crafted recipe not only tantalizes the taste buds, but also promotes an overall well-being, harnessing the natural potency of pure essential oils such as lavender, lemon, peppermint, and basil. In Carrie's cookbook, she emphasizes the quality, flavor, and simplicity, guiding you through detailed, easy-to-follow instructions with beautiful photography and expert tips. Whether you're looking to elevate your everyday meals, explore new flavor horizons, or embrace a healthier lifestyle, Carrie's cookbook is your ultimate guide to enriching your kitchen and your life with the magic of doTERRA essential oils. If you are interested, there's a link in the description.